All right. Hydroboration-oxidation. All right, let's take a look at section 8.8, which deals with hydroboration-oxidation. And what hydroboration-oxidation is a two-step process, which are shown here, step 1 and step 2. And what we end up doing is adding water across a double bond with anti-Markovnikov regioselectivity. So instead of Markovnikov, where the rich get richer in hydrogens, now we have the hydroxyl going to the less substituted position. And again, take special note that this is a two-reaction sequence. Step 1 is to treat the molecule with borane. BH3 is called borane. And THF, which is an acronym for tetrahydrofuran. It's this molecule here. I can just draw it for you quickly. It's this molecule. And then in the second step, you use H2O2, which is hydrogen peroxide, and sodium hydroxide. So two steps, borane and THF, and then hydrogen peroxide and sodium hydroxide. And you might be wondering, hey, Mr. Dion, what's this little dot? What's this little dot here in the middle? Well, I'll get into that in a little bit so that you know what that dot means. Anyhow, check it out. It says hydroboration-oxidation is a stereoselective reaction. And what we mean by that is that the hydrogen and the hydroxyl are added in a syn fashion. So the regioselectivity was that the hydroxyl goes to the less substituted carbon. And now for syn addition, what it means is that the hydrogen and the hydroxyl are going on the same face of the molecule. So let's say you added water across this double bond where you produce two new chiral centers. The hydrogen and the hydroxyl are both either going to be pointing up, they're going to be cis with each other, or they're both going to be pointing down. Again, cis with each other. And we call that syn addition. They're added to the same face of the molecule. Anti-addition is where one group is added on one side, the other group is added on the other face. And so we would not see either of these stereoisomers where the hydrogen is up and down, or trans, I guess, to the hydroxyl. And then we would not see this either. Again, it's stereoselective. We only see syn addition. So regioselectivity and stereoselectivity. We have to take both of these things into account when we're talking about hydroboration oxidation. Well, let's move on from there and talk about this mechanism in a little bit of detail. So we talked about carbocations earlier today. We said a carbocation was sp2 hybridized and that it had an empty p orbital. Well, borane, and borane is BH3, borane also has sp2 hybridization for the boron, and it also possesses an empty p orbital, much like a carbocation. So what that means is that the boron can actually stabilize itself by reacting with another molecule of borane to form something called diborane, which reveals this kind of interesting 3-center 2-electron bond. Now, I'm not going to ask you any kind of essay questions about a 3-center 2-electron bond, and there's several examples of that in organic chemistry. This is the only one you'll see in our class. But instead of writing BH3 THF, so the first step I told you was BH3 with tetrahydrofuran, and I told you that the second step was hydrogen peroxide and sodium hydroxide. Sometimes, instead of writing it that way, especially with the ACS, they'll write it as B2H6 in the first step, and the second step is being H2O2 and sodium hydroxide. And again, the reason why is because the borane will react with another molecule of borane to make this kind of B2H6 thing here, which we call diborane. So B2H6, and again, we call that diborane. So more about that BH3 with the dot in the THF. Okay, you can see my dot's in the wrong place here. It should actually look like this, BH3 with a dot in the middle and then THF. And what that means is that the borane, the BH3, is being stabilized by THF. So the borane is essentially acting as a Lewis acid, and the THF is acting as a Lewis base, and is donating a pair of electrons to make this complex. So we call this a borane THF complex here. So the little dot in the middle means that it's complexed together by a bond. It's nothing more than a way to stabilize the borane in an ether solvent, of which and THF is a borane solvent. So again, to repeat myself, in our textbook, he's always going to have BH3THF, but if you're reading the ACS study guide, they'll usually put B2H6. They both mean the exact same thing. All right, so we've got that out of the way. Why does the hydroboration occur with anti-Markovnikov regioselectivity? There's actually two good reasons why. One is a steric effect, and the second one is an electronic effect. Let's take a look at the electronic effect first. If the double bond in our alkene does a nucleophilic attack where it attacks the boron, which has an empty p orbital, what that does, when it kind of makes this partial bond here, it would mean that your positive charge is going to be on the more substituted carbon. We know that's preferential to having a partial positive charge on this carbon. And so not only do we get this nucleophilic attack occurring, but we get a simultaneous hydride shift that results in the boron being added to the less substituted carbon. Again, the electronics are nothing more than here we see the partial positive charge on the more substituted carbon. However, since the borane is bigger than a hydrogen, right? BH2 is bigger than just this little hydrogen. It stands to reason that based on sterics, that this is going to be the way the borane is added across the double bond. And so the borane adds over and over to make what's called a trialkyl borane. I'm not going to ask you about the trialkyl borane, but you may want to go into the textbook and look at the mechanism carefully to see how the trialkyl borane is produced in detail. Again, this is showing the steric consideration, that the BH2 is bigger than the H, and so that is why it ends up on the less substituted carbon, like this transition state, whereas here you can see it's much more crowded. So again, this leads to anti-Markovnikov addition across the double bond. Here's the mechanism. I'll even write it on the slide. Will not ask. Okay? I'm not going to ask you this mechanism. However, so I'm not going to go over it in detail. However, it's one of those mechanisms that I think is a good idea for you to take a look at so that you have an understanding of how it works. But again, it's not something that we ask in organic chemistry for non-chemistry majors. So back to this whole idea of syn addition. If hydroboration oxidation is syn addition, that means we have to be careful when we're drawing our products. If we have a compound like this one here, we have the hydroxyl being added to the less substituted carbon, and so we would end up with a pair of enantiomers. We would end up with a 50-50 mixture of R and S. Whereas if we have two chiral centers, then we can end up with a pair of enantiomers as well. Check it out. If you do the syn addition across this double bond, then you can add both the hydroxyl and the hydrogen pointing down, or both of them pointing up, and you still end up with a pair of enantiomers. And thus, whenever we're doing hydroboration oxidation, we have to take regioselectivity and stereoselectivity into account. With all that in mind, let's try one last practice problem for today. It deals with hydroboration oxidation. And it says, predict the products of the following reaction. Taking this unsymmetrical alkene, we're treating it with borane and THF in the first step, followed by hydrogen peroxide and sodium hydroxide. Remember, it's anti-Markovnikov addition. It's not the rich getting richer. It's this carbon that's going to take the hydrogen and this carbon that's going to take the hydroxyl. So let's pencil in what it will look like. Start by drawing our 5-membered ring. Oops, that's not a very good 5-membered ring. There we go. That's a little better. Now, we didn't change this bond over here. We didn't touch this side at all. But now we're going to have the hydroxyl pointing down and the hydrogen pointing down. That means that this methyl group is going to be pointing up. And we can have the other scenario where we draw this the same way again. I'm going to run out of space here. Let me delete this, okay? Now we're going to have the hydroxyl pointing up and the hydrogen pointing up, which means the hydrogen pointing up like that, which means that the methyl group will be going down. And the relationship between these two compounds is not enantiomers, but because there's another chiral center in here that's always pointing up. And so the relationship here would be a pair of diastereomers. And again, anti-Markovnikov addition, and it's syn addition. So here it is summarized here. We don't end up with a pair of enantiomers because we already have a chiral center in our molecule. Let's take a look at another practice problem here. Anti-Markovnikov addition of water, because both of these involve an alkene that's undergoing hydroboration-oxidation. In the first one, this is the carbon that's richer in hydrogens, so it's going to take the hydroxyl, and this one's going to take the proton. Thus, we're going to end up with something that looks like this, where we have a hydrogen going down, and then we have the hydroxyl going down like this. Now, this is not a stereocenter, so there's no need to even draw the hydrogen on a dash there, so I'm going to erase it. But we also end up with a scenario where the hydroxyl would be pointing up like this. And so in this case, we end up with a pair of enantiomers. And in the case in the bottom, we end up producing no stereocenters here. 1, 2, 3, 4, 5. This is not a chiral carbon, neither is this. And so the only consideration we have to take into account is regioselectivity and its anti-Markovnikov addition. Therefore, we just end up with this alcohol, and we would call this a primary alcohol because this methylene is attached to only one carbon. That's something that we see in organic chemistry too, primary alcohol classification.